Okay, so this is episode 3 of the Electromagnetism series, where we're going to be talking about the idea of the solenoid, okay? So coming back to what we were talking about before, we started the previous episodes, by talking about the right-hand rule. And before I talked about the right-hand rule, even the examples we use on the right-hand rule was about what? It was about a wire which carries a current, okay? And we said that there is a magnetic field all around the wire that is carrying a current, okay? So, a magnetic field lies around a wire carrying a current, right? This means that, let me take some nice colors over here. Great. If I have a wire over here, okay? Let's say this is a wire. And this wire is carrying current. Now, we said that yes, the magnetic field around can be clockwise or anti-clockwise. Yes, we did say that to use on the right-hand rule, okay? But in reality, that was just to determine the direction of the magnetic field. Does this mean that the magnetic field around the current-carrying wire is just this? No, it's not actually like that. Okay, just because we draw it like this, that does not mean that the magnetic field around the current carrying wire is just this. No, this circle that we draw is just to show the direction of the magnetic field, but this is not actually the magnetic field. The magnetic field around the current carrying wire is distributed all around the wire, okay? This is the magnetic field, okay, around the current carrying wire. It's distributed all over the current carrying wire, okay? Now, the problem with this is that because the magnetic field is so distributed around the current carrying wire, it's not that strong, okay? It's not so concentrated, okay? And when we found out that we have something like electromagnetism, where we have a wire that can conduct electricity and induce magnetism, this can be very useful in our daily lives, okay? So they thought, what if, okay, we wrapped this wire around a coil, okay? Because doesn't it make sense that this wire, which is very long, okay? This wire, which is very long, the magnetic field around it is very weak, because the magnetic field is as big as the length of the wire. It's all scattered. But if I keep, let's say the wire is 6 meters, okay? If I keep the length of the wire the same, but I just, somehow curl up the wire into loops, okay? So now the wire is still going to be 6 meters, okay? But what I've done is that I've curled the wire up into loops. Now, this way, the magnetic field around the wire is much more concentrated, okay? Because I have reduced the distance between the wire by curling them all together. So we have magnetic field at many points over here, all scattered. Over here, they're all together, okay? So the magnetic field around the solenoid, this is what we call solenoid, by the way, it is much more concentrated, okay? Actually, let's not go to solenoid directly. Let's first try to understand the idea, okay? So we have a wire which has a magnetic field all around it, okay? We talked in the previous video that the current carrying wire has a magnetic field, but this magnetic field is too open. I need to make it more concentrated. What can I do? Keep it 6 meters, okay? But I just want to compact it together into like springs, okay? When I reduce the space, or let's say enclose the wire together, the magnetic field becomes much more concentrated and strong, okay? And this is the idea of the solenoid. Give me 1 second. So the solenoid basically is loops of a wire that has a magnetic field around it, okay? So let's write the definitions and the notes over here now. Starting from here, okay? On a single wire, okay, the magnetic field is what? It is all across the long wire, but it is weaker, okay? It is all across the long wire, hence it is weaker, right? Because there's too much surface area, okay? Because large surface area that it is spread upon, okay? Large surface area, by that I mean length of wire, it's spread upon. So by this I'm talking about this idea over here where we have a wire. So let's take this wire for example, okay? Power source, let's get to a power source, alright? And we can say that the magnetic field all around this wire, okay? The magnetic field is all around wire. Alright? Now, to resolve this problem, okay? To resolve this problem, what can we do? We can coil the wire up to decrease the distance and increase the concentration and density of the magnetic field lines. And dense magnetic field lines means it is a stronger magnetic field, okay? So, let us come over here now. Over here, what can we say? We can say that if this wire is coiled in round circles, if the wire is coiled in round circles, okay, or let's say loops, what will happen? The magnetic field will be much stronger because it is more concentrated on a smaller surface area, okay? Magnetic field will be much stronger, okay? Because it's concentrated on a smaller surface area, okay? So, in this case now, if I'm going to make a solenoid, okay, let's take a coil to wrap the wire around. Let's say this is our coil, okay? And in this coil, what I'm going to do is that this coil will generally be connected to a power source, the same thing over here, okay? It's going to be connected to a power source for that wire. And as it is connected to the power source, let us to take this and this is the same wire, but we have coiled it up into small loops, okay? Into small loops on a coil. It's connected to the same power supply, okay? This is the power supply. Over here we also have the power supply, okay? It's the same power supply, same wire. All I did is I have coiled it up into loops, okay? Now, if we look at the same magnetic field, okay? This is the distance. Let's consider this as distance of the magnetic field, okay? Magnetic field is really large over here. But now look at the magnetic field. The magnetic field, stronger because more concentrated, because smaller surface area. So what I've done over here is that I have basically taken the wire, I have decreased the surface area of the wire. Because I decreased the surface area of the wire, the magnetic field lines have become much more dense. And we know that when the magnetic field lines are dense, what happens? It produces a stronger magnetic field, okay? So, this, my friends, this right here, we have produced the solenoid. This is a solenoid. And what is a solenoid exactly? A solenoid is a type of electromagnet. Again, when we were defining the definition of electromagnetism, what did we say about electromagnetism? We said electromagnetism is when electricity can produce magnetism and magnetism can produce electricity. So an electromagnet is a device that can produce or induce magnetism on electricity or induce electricity on magnetism. How is that? We're going to study that later on in the topic of electromagnetism itself, or let's say the topic of electromagnetic induction, when we learn how a solenoid, using just a solenoid, we can put magnetism on electricity or electricity on magnetism. It comes in electromagnetic induction. We'll take care of that later, but a solenoid is basically a type of electromagnet, okay? Again, electromagnet, it has electricity in the wires, it has a magnetic field around it, so it has both electricity and magnetism. It is an electromagnet, okay? And that was it for episode 3 of this series. Again, like I said, we have explanation, summary, explanation, summary, explanation, summary. So this means that the next video, episode 4, is going to be just a quick summary about everything I explained over here, and then we're going to move to the next topic, okay?